Hello, I'm Taffy Albina from Toyota Research Institute.
And I'm Crystal Lanza from Open Robotics.
And we're here to talk about supercharging the Jaguar 4x4. First, we'll give you this picture of the Jaguar 4x4 and introduce the project. We have this hardware platform, and we're going to talk about the software we wrote for it, a base node, a manipulator node, a camera node, and navigation for this product, and then we'll do a quick wrap-up. So first, the platform. It's a Dr. Robot Jaguar 4x4. It's an outdoor wheeled mobile base made by a company called Dr. Robot. It's a diff drive, 4 wheels, although we have actually replaced the rear wheels with casters, so it's not 4 wheels. It's like a 2x4x, I don't know what it is. But, and it has axis cameras, GPS, an IMU, a laser scanner. It has a 3DOF gripper and manipulator, well, plus gripper and manipulator. And comms with this robot is over Ethernet or wireless with different IPs or ports to talk to the base, the camera, and the manipulator. Project goals. 1, partnership. TRI is funding OSRC core ROS2 development. Additionally, TRI is partnering with OSRC to develop ROS2 projects for TRI. We wanted to get experience building a ROS2 robot. We wanted to answer a couple of questions. Is ROS2 at a point where a robot can be controlled via a joystick? Is it at a point where a robot can complete navigation tasks? To answer these questions, we use the Jaguar 4x4 since it's an existing platform that allowed us to get started early while we're making our own custom hardware. And we've open sourced all the code for the ROS2 version of the Jaguar 4x4, and you can see the link there. Just a quick block diagram. So we have a comms layer to talk to the robot, and then we have a base node and an ARM or manipulator node. Base node is controlled either by twist, going through the joystick, or by nav. The ARM is controlled by a joystick. And then there's a axis camera that puts out JPEG and a node to convert that JPEG to raw data. So the rest of the talk will go into detail on this block diagram, and we'll discuss some problems that we encountered, how to get multiple ROS2 callbacks executing in parallel, how to use ROS2 parameters for tuning, and how to write new style ROS2 launch files.
All right, so I'll start by talking about what we did for the base here. For the base, we wanted to do the normal stuff you want with a robotic base. So get feedback from the robot, encoders, IMU, temperature, GPS, all that good stuff. We wanted to, of course, be able to drive the robot, and then, like we said, autonomously drive a set distance. So the 2 repositories that are sort of involved with the base, there's the comms layer. The common comms layer is in the top one, and then the base node, the ROS2 base node is in that bottom one. So that shared comms library, the reason we made it a library is because the protocol that you use to talk to the base and the ARM is exactly the same. So we just made a library, and both of them link against it. There's a lot going on sort of in the base, so it's a threaded node. We use futures and promises, the C++, either 11 or 14, I don't remember, futures and promises to communicate with the threads about starting up, shutting down, that sort of stuff. One of those threads is a ping thread, of course, which it's sort of a safety thread, right? It make sure that we're still talking to the robot, and if that stops, then we stop accepting all commands and attempt to send an e-stop down to the robot motors. There's also, of course, getting into the ROS2 stuff, there's the twist callback where we take the command vel, twist in, and convert it to motor powers. There's the joystick callback to do software e-stop, which I'll talk more about in a minute. There's also the opportunistic gyro bias. So I call it opportunistic because the gyro on this platform tends to drift a lot. So anytime the robot is stopped, we actually take a bias reading to get an offset, and so we can apply that offset to any future gyro readings. and of course, we do simple position updates from odometry, and then in the end, to do the sort of driver set distance, we have a service. So talking more about that e-stop, the reason that's kind of interesting is because we wanted the software-defined e-stop to work in all situations. The robot has, of course, a hardware e-stop, but that cuts power, right, and we have to restart everything, and so it's pretty annoying to use. So for most of our development, we want to have a software e-stop. And originally, we just naively subscribed to the joystick channel, and we had a button on the joystick. And when you hit the button, it would stop all commands and send e-stop down to the robot. And that works, except that it doesn't work in all contexts. In particular, it doesn't work if you have a long-running service or a long-running topic going, because by default, ROS2 services all the services and topics on a single thread in a single queue. So the solution here is two parts that ROS2 has for this. One is the multi-threaded executor, so you can have multiple threads servicing callbacks. But on its own, that's actually not enough, because there's still only a single queue, and you would still be while you had multiple threads, the threads would still be blocked on the queue, waiting for the other service to finish. So in addition to the multi-threaded executors, you also add in the callback groups, which you've heard a little bit about previously. And so all the callbacks in a particular group are handled by a thread. So basically what we did is we made the base node have all callbacks on one thread, except for the joystick node for e-stop, which is handled on a separate thread, or a separate callback group. Sorry, to be clear, a separate callback group. And this is just some of the code to do it. In main, you end up creating a multi-threaded executor, and then you instantiate your ROS2 node, and then you add that node in and spin on the executor. So that's just the multi-threaded executor. So in the Jaguar4x4 constructor, when we actually go to make the subscription to the joystick, you'll see we call create callback group, which creates a new callback group, particularly for the joystick, and then when we instantiate the subscription, we use that callback group. One small subtlety here is that you have to hold a handle to the callback group, otherwise it'll be destroyed and will not work as you expect. So, yeah.
Oh, I have this one. Just a quick discussion about the manipulator node. The goals for this one were to be able to get feedback from the manipulator, the encoders, et cetera, to drive the manipulator via joystick, and to autonomously move to a particular position in space. The code for that one is in that repository you see there. This is also a from scratch C++ ROS2 node. It uses the shared comms library with the base. It has a joystick callback for the e-stop, and also buttons to move the shoulder and elbow joints. Uses the same threading concept as the base and the same ping thread concept as the base. And we wrote a service to home the manipulator joints. So in order to move to a specific place, you need to know where the arm is. And in order to do that, we needed to calibrate the manipulator position. There's not a home position by default. So we were able to calibrate the shoulder joint, the one you see down there in blue, by using encoder feedback. So move it until it's going to rest in its base, and then check the encoder counts and say, oh, it stopped, we must be homed, we're happy. We couldn't do the same thing for the elbow joint. It was not a robust enough joint. We kept basically popping it out of its socket. So our lesson learned here was that we can't actually calibrate this arm automatically. So you have to joystick to a home position before you can control the arm autonomously. There's also a camera, which you can see right on top of the gripper. It's circled in blue there. It's an Axis camera, Ethernet camera. Came with a ROS1 driver, and we ported that to ROS2, and you can see our port there at that repository. Camera outputs JPEG, and we wanted to use those images, and so we wrote a node to convert the JPEG to RAW. That's our Python node. I think it's our only Python node in here. And that's also available on the repository.
All right, so I'll talk just a little bit about the navigation. Actually, I'm going to go, since we're a little short on time. So for the navigation, right, as I said, we wanted to go to a goal pose and navigate over a short distance. So we didn't really need anything that did closed loop. So we just used the odometry and IMU to navigate over a short distance. We did this as a service. It's actually a separate node with a service. So that, with that, we also made a bunch of parameters on the node so as we were developing the node, we could easily tune the constants, and the code is listed there. I want to talk a little bit more about parameters. You've seen a few things about parameters already. So I think the one thing that's different here from what you've seen before is you can see there in the class constructor that we call set parameter if not set. So what this ensures is that it ensures that the parameters show up when the node starts, no matter what. So in ROS2, we can either set parameters through the command line functions ROS2 param, set, and get. We can list them, but they can also be set from the command line when you're launching the node in a YAML file. So the set parameter if not set, right, if the parameters come in from the YAML file, set parameter not set is essentially a no op. But if they're not set in the YAML file, if you're just launching it to see what happened, it'll take those sort of default parameters, and then you can modify them later. So this whole setup there, and then going to where we use it in the go to goal XY, we go and get the parameter and then into those variables, and then we can use them. So this whole setup here means that while you're developing, you can easily switch the parameters up as you want by setting them and getting them and tweaking and tuning. And then when you find a set of constants that you like, you can put it in the YAML file and they'll just launch it with that. And that way, they'll always be what you want without having to recompile your code for it. And then, so talking about launching, then again, you've seen a lot about launching already today. The one difference here I'll show. So this launch file launches a couple different things. This one launches the base and the teleop twist joy. The important bit is that if you see on the teleop twist joy when it does launch ros.actions.node, the arguments it passes is the __ params : equals, and that allows you to pass that YAML file in and get those parameters at launch time. So, and then we have a couple videos. We'll see if they work. About the first video, right? We're just calling the service on the navigation node to go to goal post straight on. We tell it in the X 3 meters and the Y 0 meters, and let's see if this works. It does, but you can't see it. All right. Well, I'm just gonna let it go there. So yeah, right, we're just driving straight forward there, and then the other one, we're trying to hit the 2-2 off the edge there, and this one, wiggles. It's a happy robot, a little drunk robot maybe. So, oh, that's not what I meant. I did not want to play it again. All right, there we go.
So we'll talk a little bit about future work and then wrap it up. So future work, we do a little more work on the gyro and then integrate the gyro and the odometry, just do an EKF and robot pose. Make a navigation PID loop. Right now we've got a P loop. Maybe use move base and then rewrite JPEG to RAW in C++ because it's a lot slower otherwise. And then try running this with Cartographer. So just to wrap up, we created a bare bones Jaguar 4x4 system in ROS2, and there's a pointer to the sort of top of the repositories for that. We satisfactorily answered our questions about ROS2 usability. Yeah, we can do joystick control, we can do nav, everything done in ROS2 on a robot. We're continuing to develop a more full-featured system on custom hardware. We'll continue to release software to the ROS2 community. And we're going to continue the TRI OSRC partnership and ROS2 collaboration. Thank you.
Thank you.